So let's just quickly prove this to ourselves using the graphing calculator, just so that we don't have to rely on these hand drawings. And let's first look at even polynomials. So we'll graph y equals x to the second power. We'll graph y equals x to the fourth power. And likewise, we'll graph y equals x to the sixth power. And you can keep going if you want. So the lowest power one will be blue, then the quartic will be red, and the sixth degree will be black. So let's graph these, and we'll look at zoom standard, so zoom 6. And you can see the blue one is the parabola, that's the widest. The red one, that's the quartic, it's much skinnier, but the black one, the sixth degree one, is the skinniest. And we can even zoom in. Let's change our X window here. Let's say we're going from -4 to 4, and we can change our Y scale even. The negatives we can leave the same. We can make this a scale of, let's say, 30. And we'll make the tick marks go by 5, just so that they're not all bunched together. And it's much clearer here. The parabola is the widest, the quartic is in the middle, and the sixth degree is the steepest of them all. And of course, like I mentioned, the higher the power of x, so if we put in x to the 8, the steeper it becomes. So that's this pink curve here. So that is when x is raised to an even power, and we're just looking at these parent functions here, so we're not adding or subtracting any terms here, we're not multiplying out in front. And so now let's look at the odd power terms just to prove that to ourselves. So we're going to clear all of these out here. And let's just go back to the beginning. We're going to plug in when x is raised to the third power. We'll look at when x is to the fifth power. And we'll go as far as x to the seventh power. Now we'll go back to our standard zoom. And we can pretty much see that that conclusion was correct, that the blue one, that's the cubic, that is the least steep. The red one is the fifth degree, and the black one is the seventh degree. Now, if we want to get a better picture, let's essentially close our window a little bit. So we'll go from x values of -4, let's say, to +4. And our y values, let's say we'll go from -30 all the way to 30. We'll change our tick marks. This time, let's just do 10. And we'll graph it. And now it's much clearer. The blue one, again, that's our cubic. The red one, that's our fifth degree. And the black one's our seventh degree. And if we went one step further and looked at x to the ninth power, then that's the pink one. That is the steepest out of all of these. So the general conclusion with these two patterns we notice is that, let's say we have some random polynomial where y is a function of x, and we have, let's say, x to the fourth plus 2x to the third minus 7x squared plus 8x minus 14. Some random polynomial. And when we're considering what the graph looks like, we can consider a concept called end behavior. And that's basically asking what happens to this function as the x values get really large. And what you can imagine, as x gets bigger and bigger, so as it approaches infinity, that basically the term that tends to dominate this function is the highest power term. Because if you imagine, let's say we're plugging in 10 to the 8th power, so 1 followed by 8 zeros, it's 100 million. And we raise that to the 4th power, this is 10 to the 32nd, or 1 followed by 32 zeros. Whereas if we look at this term, 2 times 10 to the 8th cubed, this will be 2 times 10 to the 24th. So a 2 followed by 24 zeros. Well, 1 followed by 32 zeros is way, way bigger than 2 followed by 24 zeros. In fact, it is about 100 million times bigger. So you can imagine adding 2 to 100 million and convince yourself that adding 2 to 100 million doesn't really change the fact that it's 100 million. So as x gets bigger and bigger, this difference is going to get larger and larger as well. And so in the end, for these really large, or when x approaches negative infinity, these really negative values, The only term that really matters is the highest power term. And even if it's multiplied by a constant, that doesn't really make too big of a difference. The main thing that does matter is that this is to the fourth power. And so we would say the end behavior, what this function looks like when you zoom really far out, is that it's going to look like this type of polynomial here, like the parent function for y equals x to the fourth. And we can see that if we look at the graph of this. So let me just delete some of that marking. And let's plug this into our graphing calculator. So we have x raised to the fourth power. Now we'll get out of the exponent plus 2x to the third. And make sure you're always clearing out of that exponent or else you'll continue writing as an exponent. We have minus 7x to the second plus 8x and then minus 14. And we'll start with a standard zoom and then zoom really far out from there. So we don't really see too much, so let's zoom out. And we'll just keep zooming out so that we can get a better idea of what this graph looks like. So it looks like we should maybe zoom in on the x values, but we can leave the y values as being really large. So let's say from minus 10 to 10. Sometimes the hardest part of these functions is just finding the right scale for these. And we'll use, let's say, 20 for the tick marks on y. And so you can get a general idea of what this looks like. But notice, and let's just zoom out even further. Change our y values. We'll go from minus, let's say, 500 to 500. But what you can notice is that it will start to look like a quartic function the more you zoom out. So let's do tick marks of 100 here. Again, now you can see it's even flattening out more and more. And the more we zoom out with our y values, the closer it will start to look like that quartic function. So what I was saying is that when looking at this from a very zoomed out view, when looking at the end behavior of this polynomial, the only term that really matters is the highest power term. And if it was negative, basically what that does is just reflect all the y values down. Putting a negative here essentially makes the y values negative when you plug in whatever your x value is. So to go back to our original questions here, we mostly just need to look at this highest power of x and determine what the parent function for, let's say, x to the sixth looks like. And that's generally what this graph is going to look like.